Okay, here we go. I'm trying this to see if it's helpful. I'm dressed for a Sunday, so apologize for that, and I apologize that my dryer is going to keep making this beeping noise, but let's see if it helps. We're looking at section 1.2, algebraic limits and continuity. So straight out of the book, it tells us that theorem 2 is limits of rational functions. Basically, if we're looking at the limit as x approaches a, and a is an actual number of f of x, then that is equal to f of a. In other words, plug and chug, which is what my own favorite calculus teacher told me many, many years ago. So, for example, we're going to use the theorem of limits of rational functions to find the limit, and if necessary, we'll state that the limit does not exist. So, I want you to notice that we're looking at the limit as x approaches 5. And so what that's telling me is we're going to use x equals 5, and we're going to plug it into the function. So instead of 5 times x, we'll have 5 times 5 plus 1, which is 25 plus 1, or 26. And so the limit of our function as it approaches 5 is 26. All right, we're going to find the given limit again. Notice that we are approaching -1. So we will be substituting -1 for x. And one of the things that happens here is that people want to use this negative as the negative from 1, but it's not. It's a negative in front of the x, which is -1, to the second power, plus 6 times -1 minus 7. Then we'll have -1 times -1 is +1, but we still have that negative on the outside. You're probably comfortable with that, but it's easy to forget, and I just want to make sure that you remember it. Then we'll have 6 times -1, which is -6 minus 1. And then -1 minus 6 minus 7 gives us -14, which is the limit of the function as x approaches -1. We want to do the same thing here. This time, however, I want you to be a little careful. Again, we are approaching a number. We're approaching -10, so we're going to be substituting in -10. But if we plug -10, excuse me, into the denominator, -10 plus 10 becomes 0, and the whole function is undefined. So when we're looking at something that is in rational form, I say first you want to factor the numerator and the denominator to see if, in fact, anything will cancel. Well, in this case, it does, because x squared minus 10 is a difference of squares, and that gives me x plus 10 times x minus 10. And on the bottom, we just have the x plus 10. Now, look at this. The x plus 10 and the x plus 10 cancel each other out and give us just x minus 10 to work with. So that eliminates that the negative 10 will make this undefined. So when we plug in the negative 10 for x, we'll see that as x approaches negative 10, that it equals that the limit is becoming negative 20. And I want to say that you need to remember that the limit is approaching negative 10. So there may be an asymptote there. There may be a hole there, but it's approaching negative 10. And by the theorem of limits of rational functions, we can do this plug and chug. But I want you to understand that it is approaching, and that's why if we plugged it straight in, it blows up, it becomes undefined. But when we take out that part of the function that we're looking at for the limit, we'll find that as it approaches the negative 10, that the limit is negative 20. Now the game changes a little bit when you have the limit approaching infinity or negative infinity. So this is different. So you can see here that we have the limit approaching positive or negative infinity for all these things. And so we have three different things to consider. If we're given our f of x equal to, and this is what we're looking at, ax to the m exponent, bx to the n exponent. I want you to also remember that we are implied to have both the numerator and the denominator in descending order. And so we're looking at the leading term, and one of three things can happen. If both the leading terms in the numerator and denominator are the same degree, which means their exponents are the same, then we're going to end up with a fraction, which is composed of the leading coefficients. If we're in a situation where m is less than n, where the top degree is smaller than the bottom degree, then our limit will be 0. If we have m greater than n, meaning that our numerator degree is larger than our denominator degree, then that's when we would say that the limit does not exist. So let's look at our example. You can see that the limit is approaching infinity. The first thing we look for is the degree. So the degree of the numerator is 3, the degree of the denominator is 3. So we're in an m equals n situation because our exponents are the same. So we'll say that our limit is 12 over 28. But just like you almost always have to do, you do want to reduce the fraction. This reduces by 4 to give us 3 over 7. So as x approaches infinity of that function, because our leading degrees were the same, we looked at the leading coefficients, and that's our answer. We're going to do the same thing here, noticing that the limit is approaching infinity. So I'm going to look at my leading terms. And again, they're both degree 1. So we're in the m equals n situation again, which tells me that the limit is 5 over 8. And we would plug that in. And you know what? We would miss it. The reason we would miss it is because we always need to look at the blue after the answer, because that's what tells us how to put the answer in. So it wants the answer as an integer, a positive or negative whole number, or as a decimal rounded to the nearest thousand. So I'll be the first to say I would have jumped with 5 over 8 and plugged it in. But if I say 5 divided by 8, that'll give me 0.625. And that will give me the correct answer in the answer box. So make sure that you always pay attention to how it asks you to write the answer. We want to find the indicated limit, and notice that this time again, we've switched. We're not looking at infinity anymore. We're approaching a whole number. So this goes back to our plug and chug. So we are going to use x equals 9, and we're going to plug it into our function. So we'll have 7 times 9 minus 2, which gives us the square root of 63 minus 2, which is the square root of 61. Before you do anything, pause, and you know that we're not going to choose B because we obviously have a limit that exists, but we're going to choose A, and it tells us it wants us to use radicals in our answer. So we're not going to figure out what the square root of 61 is. We're simply going to type in the square root of 61. And so that's our limit as x approaches 9. One of the other things in this section that we need to look at is continuity. And so this is an example of a continuous function over the interval -6 to 6. If you aren't familiar with interval notation, or if you're kind of still rough on it, you're not quite sure, you need to spend some time reviewing interval notation, because throughout the course we'll be writing our answers using interval notation. So as you can see, this is a very smooth curve. There are no asymptotes, there are no holes, And we can't talk about what's happening outside of the interval from -6 to 6, but between -6 to 6, we can say that it is definitely continuous. This is a perfect example of a non-continuous function over the same interval from -6 to 6. Because although it is smooth, if you look right here, when x is equal to 1, it jumps. So it is not continuous. Think of continuous as just a smooth, wonderful example. And then the last thing I want to talk about is using this graph to answer the questions. So for A, when we want to find the limit of f of x as x approaches 4, notice the plus in the exponent place. That means from the right. So from the right, going this direction for the 4 plus, at x is 4, it's approaching this y value. And that y value is 1, 2, 3, 4, 5, 6. So the limit as x approaches 4 with the positive in the exponent, that tells us that the first answer is 6. The next question is, what is the limit of the function shown as x approaches 4? This time the negative tells us from the left. So that means in this direction. So as we're looking at our function, we're approaching here. And so that gives me the y value of 4. So we're approaching from two different sides. So if it's from the right, our answer is 6. If it's from the left, our answer is 4. In question B, it wants to know what is the limit as x approaches 4. In this case, the limit does not exist. The reason we say the limit does not exist, because to be the limit, it has to be approaching the same number from the left and from the right. And in this question, we can tell from the answers in A, since they're different, the limit does not exist. Had they both been approaching the same number, then that would be the answer to B. Now, for C, if we want to know f of 4, you probably remember this, but it's f of x equals y. So it's telling me when x is equal to 4, what is y? That's what it's asking me. So when x is equal to 4, we've got two choices. We've got the 6 and we've got the 4. Because the 4 is an open circle, it's not there. We have to choose the closed circle because that tells us that at when x is 4, that it is at y equals 6. So our answer to C is 6. And then to answer D, is f of x continuous at x equals 4? Well, we saw looking at the limits that it's not. We see by just physically looking at the picture that it's not. So the answer to D is no. And it will be a multiple choice question. But in my mind, the way that I remember it's not continuous is that it jumps. So that is a summary of section 1.2. I would appreciate feedback on it if you thought it was helpful and if it helped clear up the limits for you. Have a great Sunday. I'm going back to my other stuff.